Welcome back to the channel. Today we will start with part 6 of Applied Physics 1, and we'll cover about fiber optics. Let's get started. Fiber optics is a technology that uses light to transmit data, images, and sound over long distances through optical fibers. These fibers are made of glass or plastic and are designed to guide light along their length by using the principle of total internal reflection. Fiber optics are widely used in telecommunications, internet connections, medical imaging, and data transmission due to their ability to carry large amounts of information quickly and over long distances with minimal loss. Basic structure of optical fiber includes a core, which is the innermost part of the fiber, made of high-purity glass or plastic. This is where light propagates. Cladding is a layer surrounding the core with a lower refractive index, which helps keep the light confined in the core through total internal reflection. And coating, protective layer that shields the fiber from external damage. Numerical aperture is a key parameter that determines the light-gathering ability of an optical fiber. It describes the range of angles at which light can enter the fiber and still be guided through the core by total internal reflection. Diagram of numerical aperture shows a fiber core and cladding with light rays entering at different angles. The diagram would demonstrate which angles result in total internal reflection and which do not. NA is given by the following formula, where N core is the refractive index of the core. N cladding is the refractive index of the cladding. Interpretation. Higher NA allows the fiber to accept light at a wider range of angles, making it easier to couple light into the fiber. Lower NA narrows the range of acceptable angles, leading to more efficient guidance of light with less dispersion. Optical fibers can be classified into step index and graded index fibers based on the way the refractive index of the core and cladding is structured. In step index fibers, the refractive index changes abruptly between the core and the cladding, forming a sharp step in the refractive index profile. Core has a uniform refractive index. Cladding has a lower and uniform refractive index than the core. This type of fiber supports two modes. Single-mode step index fiber. It has a small core diameter and allows only one mode, light path, to propagate, minimizing dispersion and making it suitable for long-distance communication. Multi-mode step index fiber. It has a larger core diameter, allowing multiple modes to propagate. This can cause modal dispersion, where different light paths have different lengths, resulting in signal distortion over long distances. Step index fibers are simple to manufacture and are often used in short-distance communication systems and sensors. A step index fiber diagram shows a sharp boundary between the core and cladding, with light rays reflecting off the boundary through total internal reflection. In graded index fibers, the refractive index of the core gradually decreases from the center of the core to the cladding. This creates a parabolic or curved refractive index profile. The light rays in graded index fibers follow curved paths instead of bouncing sharply off the core cladding boundary. Core. The refractive index is highest at the center and decreases gradually towards the outer edges. Cladding has a uniform refractive index, but lower than the outermost core refractive index. Advantages. Reduced modal dispersion. In graded index fibers, different light modes take curved paths, but the varying refractive index ensures that light rays near the outer edge of the core, traveling a longer distance, move faster than those near the center, traveling a shorter distance. This balances out the time differences between the modes, reducing dispersion and allowing for higher bandwidth. Graded index fibers are widely used in telecommunications and local area networks, LANs, due to their ability to transmit data over moderate distances with minimal signal loss and distortion. A graded index fiber diagram shows the gradual change in the refractive index from the core center to the cladding and illustrate how light rays curve within the fiber, following parabolic paths. You can understand how step index and graded index fibers differs from each other based on their respective refractive index profile, light path, modal dispersion, and their applications. Attenuation and dispersion are two critical factors that affect the performance of optical fibers by limiting the distance and speed at which data can be transmitted. Attenuation refers to the loss of signal strength as light travels through an optical fiber. This loss can be due to several factors, and it limits the distance that light can travel without requiring amplification. Causes of attenuation are absorption loss. Absorption occurs when impurities in the fiber material, such as hydroxyl ions, OH, or defects, absorb some of the light energy, converting it to heat. This is a material-dependent loss. Intrinsic absorption, due to the glass material itself, where atoms like silicon absorb light at specific wavelengths. Extrinsic absorption, caused by impurities in the fiber, such as water vapor or metal ions. Scattering loss. Rayleigh scattering is the primary form of scattering loss in optical fibers. It occurs due to microscopic fluctuations in the refractive index of the fiber material, which scatter light in different directions. This scattering is more prominent at shorter wavelengths and is a key factor limiting fiber performance in the visible range. Bending loss. Light traveling through a fiber can be lost if the fiber is bent too sharply, causing the light to escape the core. This is known as macrobending loss. There is also microbending loss, which occurs due to small, random bends in the fiber caused by manufacturing imperfections or external stress. Impact. Attenuation results in signal weakening over long distances. To overcome this, repeaters or amplifiers are placed at regular intervals in long-distance communication networks. Dispersion refers to the broadening of the light pulse as it travels through the fiber, which causes overlapping of signals and reduces the clarity of transmitted information. It limits the bandwidth and affects the speed of data transmission. Types of dispersion are modal dispersion. This occurs in multimode fibers where light travels through the fiber in different paths or modes. Each mode takes a slightly different time to reach the other end due to varying path lengths. As a result, the light pulse broadens, causing intersymbol interference, which limits the data rate and the distance that can be transmitted without distortion. Chromatic dispersion. Chromatic dispersion occurs because different wavelengths of light travel at different speeds through the fiber material. Since optical signals are not purely monochromatic, different wavelength components arrive at different times, causing pulse broadening. This can be further classified into material dispersion, arising from the varying refractive index of the fiber material for different wavelengths. Waveguide dispersion, due to the dependence of the light's velocity on the fiber's geometry. Polarization mode dispersion, PMD. In single-mode fibers, polarization mode dispersion occurs due to the asymmetry in the fiber core, which causes different polarization states of light to travel at different speeds, leading to pulse spreading. Impact. Dispersion causes signal distortion and limits the data transmission rate and distance. In high-speed optical networks, dispersion management is crucial to maintain signal integrity. Application of optical fibers. Optical fibers are used in a wide range of industries and applications due to their high bandwidth, low attenuation, and immunity to electromagnetic interference. Some key applications include telecommunications. Optical fibers form the backbone of modern communication networks, transmitting large amounts of voice, data, and video signals over long distances with minimal loss. They enable high-speed internet and telephone communication. Medical imaging. Optical fibers are used in endoscopy, where flexible fibers are inserted into the body to view internal organs. They provide a non-invasive way to diagnose and monitor medical conditions. Data transmission. In local area networks, LANs, and wide area networks, WANs, optical fibers enable high-speed data transfer between devices and across campuses, cities, and even continents. Sensors. Optical fibers are used in fiber optic sensors to detect changes in temperature, pressure, strain, and other physical parameters. They are useful in industries such as aerospace, civil engineering, and oil exploration, defense, and military. Due to their high security and immunity to electromagnetic interference, optical fibers are used in military communication systems, missile guidance, and submarine communications. Broadcasting. Optical fibers are used for cable television, CATV, and live broadcasting of events, where high-speed data transmission is crucial for delivering high-definition video signals. Lighting and decorative applications. Fiber optic lighting is used in architectural lighting, decorations, and artistic displays. It provides flexible, safe, and energy-efficient lighting solutions. In an optical communication system, light is used to carry information from one point to another. The system consists of several key components, including a transmitter, an optical fiber, and a receiver. This is the block diagram of optical communication system. Diagram explanation. Transmitter. The transmitter converts the electrical signal into an optical signal using a light source, such as a laser diode or LED. Optical fiber. The optical fiber acts as the transmission medium, carrying the optical signal from the transmitter to the receiver over long distances. It guides the light using the principle of total internal reflection. Receiver. At the receiving end, the optical signal is converted back into an electrical signal using a photodetector, such as a photodiode or pin diode. Regenerator or amplifier. If needed for long-distance communication, optical amplifiers or repeaters are used to boost the signal and compensate for attenuation losses. Output. The final electrical signal is used by the receiving system for the intended purpose. Quick summary. Fiber optics is a revolutionary technology used for high-speed, long-distance data transmission, leveraging the principle of total internal reflection. The numerical aperture, NA, defines the light-gathering ability of an optical fiber and determines the range of angles at which light can enter the fiber. Step-index fibers have an abrupt change in refractive index between the core and cladding and can be used for both single-mode and multi-mode transmissions. Multi-mode step-index fibers experience high modal dispersion, limiting their use to short distances. Graded index fibers offer a gradual change in refractive index, reducing modal dispersion and allowing for more efficient data transmission over moderate distances. That's it for today's video. We will look at other topics in our next video. Till then, please like, share, and subscribe to the channel. See you in the next video.